Hello, this is Dr. James Camp at Lee College in Baytown, Texas, and this is my presentation on how to write functions in C and C++. So first off, what is a function in programming terms? A function can be thought of as a sort of black box that takes some kind of input and produces some kind of output. In math, we define a function y equals f of x if for every x it produces some y as an output, some characteristic y as an output. So any given x corresponds to one particular y. Different x, you get a different y. You can think of this as a box F that takes an x as an input and gives a y as an output. Given that, you don't actually have to understand the inner workings of the F, though if you're taking a math class, you probably should. In programming, we think of a function as a subroutine that does some sort of operation for us on our data. So you've already seen the mathematical function y equals pow of x to the n, and learned that and this can be thought of as a black box called pow that takes an x and an n and returns a y. So we've got inputs here and an output here. The inputs are called in programming language parameters or arguments to the function. We most often refer to them as parameters when we're describing the function and arguments when we're sending them to the function. And the output is called the return value of the function. Okay, so as you can see from our power example, every function needs a few things. One, a name, such as pow or move. Okay. Two, parameters. Now, this can be 0 or more. Pow takes 2. Move might not take any parameters. It might just move your checker piece one space or something. 3, a return value. This can be only one. We cannot create functions in C++ that return more than one value. And then they need a code body that performs the named task. So in the model we've described so far, that means the function's name exists there. It takes some number of parameters as input, gives a return value as output, and in the middle, it runs some amount of code that operates on the parameters and generates the return value. So how do you implement a function in C? Actually, it's pretty easy. First, you have to define the function with a function header. Let's say we want to calculate the volume of a box. We name the function volume, and then we give it double length, double width, double height, okay. And then in between a pair of curly braces, as always in C++, we can define double vol equals len times width times height. Okay, and then very important in a function, we return the value we just calculated. So let's break down the pieces of the function so far. We've got a return type. Here, this function expects to return a double type value because volume might have a decimal point in it, especially since we're giving it a parameter list with double types. Now notice that even though all three of my parameters are type double, I have to use the word double each time I declare a parameter. I can't just say double len width height. Okay. Obviously here is our function name. And then we have to have a return statement that matches our return type. If I tried to return a string instead of a double, the compiler would yell at me. All right, now that we've written our volume function, how do we use it? Well, let's say we're down here in our good old int main. There are a lot of ways we can use our function. We can use it to initialize a new value. Double V equals volume. There's our function of, say, 1.5, 2.4, 3.3. Okay, notice that in this case, I gave literals as arguments. Now, I've told you to avoid using literals in your code because they appear as magic numbers. Nobody knows what 1.5, 2.4, and 3.3 mean. So it's better to say double A, well, let's stick with length, width, and height. L equals 2.0 over 3.0, W equals 1.0 over 3.0, and height equals just 2.5. Okay. Now I can reuse my variable v. Say v equals volume of length, width, and height. So this time I have passed variables as arguments. Notice that they don't have the same name as the parameters I defined in the function header. They don't have to. The value of L is going to be copied to the volume function and used there. It doesn't matter what L is named. I can also use these directly in other situations. So I can see out the volume is, and I can copy my volume function right here into the cout statement. Okay. And then of course I have my return 0 statement at the end. Notice that here I used a mix of literals and variables as arguments. That's also legal. You can do whatever you want inside those parentheses. Another trick is that you can, in the C family of languages, you can overload functions. So it's all well and good that we know how to calculate the volume of a box, but what if our box is a cube? Do we have to write volume of side, since they're all the same? Nah. We can write a new version called double volume, double side, and then we can say double volume equals power side 3, side cubed, return vol. Okay. Then later on in my program, I can write the code vol1 equals volume of 12.5, 24.0, 33.3, and vol2 equals volume of 33.3. And it will know which volume to pick based on what's called the signature of the function. It sees the volume name. It knows it has 2 copies of volume in this program, and so it checks the rest of the signature, whether it's got 3 parameters or 1 parameter, and it automatically matches that input to whichever function matches the number of parameters. This allows me to avoid the nasty situation of having to write functions named rectangle volume and cube volume, and that I can just have one function named volume, but have several versions of it that are what we call overloaded. Okay. There are 4 general patterns in constructing functions. The first is what I call a true or mathematical function, and that's a function that has both inputs and outputs. So this might be Boolean output is green int hue as an input. So this function would probably read an integer hue value from a color wheel somewhere between 0 and 360, and it would try to determine if that's in the green part of the spectrum, and it would return a Boolean true if it was in the green part and false if it's not. So that's a function. It's taking an input and an output. You can have an output only function in C++. This might have Boolean I see green, which doesn't have any input parameters. This you might use if you're, say, writing a robot that's supposed to scan the room to determine when it finds a green place to stop on. Maybe it's trying to find some grass to sit on or something. It would take readings from the input from the robot's sensors, so you don't need to send it any parameters. It would pull the data it needs from inside the robot. It then might call the isGreen function to determine if the sensor data is showing a green value. So it's going to do some internal work with the sensors, and then it's going to return a Boolean that says, yes, I see green, or no, I don't see green, true or false. You can have an input only function in C++. If you're not going to return a value, the function still needs a return type. The return type for not returning a value is a new keyword called void. Some people call input-only functions void functions. So I might say void go forward int % speed. So that might tell my robot what percentage of its full speed it should go forward at. It doesn't need to return a value because I can see the robot going forward, so it's a void function. It takes % speed as an input, and then it does some internal processing to make the robot go forward. Finally, we can have a no in, no out function. You can have void stop all motion. Okay, this tells my robot, okay, I want you to stop. I want you to stop moving your wheels. I want you to stop moving your scanning motor. I want you to stop everything. I don't need to give it any parameters because I'm asking it to stop everything. So it just does some internal calculations internal processes to stop all the motors from working. Doesn't need to return anything because I can see that the robot has physically stopped. Now, some programmers would like to make this a output-only function so that it returns the Boolean true if it was successful in stopping all motion and false if it didn't. But in a fairly simple robot application, I think all we need is to make this a void function. Okay. Finally, there are two special cases of functions that you won't use very often but need to be talked about. The first is a recursive function, and that's where your function func gets its input, then calls itself possibly once, possibly more times, in order to determine its output. So really I should have the output have this kind of giving itself more input. So let's see how that works. The classic example is calculating a factorial. If you remember, a factorial, x factorial, is defined as x times x minus 1 times x minus 2 all the way down to 1. Well, we could write a loop that counts down from x to 1, or we could define this recursively. Long factorial of int x works like this. If x is less than or equal to 1, fact equals 1. Forgot to define my variable here, my internal variable. Else, fact equals x times factorial of x minus 1. And then we return fact. What does this do? Well, it takes a value x. If x is less than or equal to 1, then the answer is simple. X factorial is 1. If not, then factorial is x times this whole thing happens to be the factorial of x minus 1. So we take x minus 1 and we redirect it as input to this function, which comes back to checking if x is less than or equal to 1, or if not, we recurse again and again and again. Eventually, x minus 1 will come down to 1. We'll return fact equals 1, and then we'll start running the whole series backwards, resolving factorial of 1, factorial of 2, factorial of 3, factorial of 4, until we get to x. And then that will all multiply together to form factorial, and we'll return factorial as a long. So I was wrong here. I should have declared this as a long factorial. The second, which you may actually end up using more, is the idea of a reference parameter. Let's say we have a model of a paper airplane flying through the air, and we calculate in 10 millisecond increments the path of this paper airplane. Well, if we want to write a function double fly double x double y double t, we have the problem of we've got three inputs, x, y, and t, that are all changing. Which one are we going to return? Okay. The answer is none of them. We're going to use reference parameters so that we can write void fly, and we're going to write double with an ampersand x, double with an ampersand y, and double with an ampersand t. Now, in our code, we'll perform our flight calculations to determine, the effects of drag and gravity and such, to give us, velocity in the y direction and velocity in the x direction. And then we'll say x plus equals velocity x times delta t, y plus equals velocity y times delta t, and t plus equals delta t. Okay, we don't have to return anything because we used reference parameters. That means instead of copying the value over, we actually copied the whole variable into our function, and any changes we make to x, y, and t will be reflected in the program. So if we go down to our void main, we can say x equals x naught, y equals y naught, t equals 0, and while t is less than, say, 1,000 milliseconds, we can do fly x, y, t, and the program will keep updating x and y and t for us because these are being passed by reference to the fly function. Okay, as usual, I want to end with some best practices for functions. One, start with a comment. There are a lot of different practices for this. Your book gives one that's based on the Java doc standard. A lot of people like putting a / comment just before the name of the function. This function calcs cube volume given length of a side. Okay, and then you would type your double volume, double side. Okay. Other people like using the multi-line comments, where you would type /* and then you're free to type in, as many paragraphs as you want here. This function ... blah 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 */ at the end. The Java doc style has you start with /**, and that is picked out by automatic documentation tools as a function comment that should be preserved in documentation for your functions, for your code. Okay. Two, don't modify parameter variables. Okay, unless you're passing it on purpose as a reference variable, as we covered in the last slide. Don't, inside your function, say side plus equals 1. Okay, you're not actually changing the value of side in the calling function, so it's better to, if you want to have side plus 1 for some reason, to declare a new variable, double side 1 equals side plus 1. Okay, better to create new variables than to modify the ones that you're passed. Do make sure every path returns a value. It's frequently an easy thing to do to say, if side greater than 0, return power of side comma 3. But guess what? For every if, there's an else branch, okay, that maybe you didn't deliberately put the else in there, but if you don't put in an else, there's always an else do nothing that's implied by an if statement. And do nothing does not return a value. So it's always better to structure your code with the return statement at the end of your function so that everything returns a value. So you can put double vol equals 0.0 if side is greater than 0 vol equals power of side cubed, not 33. Okay, and then return vol will return a 0 if your side was 0 or negative, and it will return the appropriate volume if your side was positive. Four, define all functions before they are used. The way we've been doing functions so far, this is not a big deal because we tend to call them from the main function, and we write all the functions before we get to the main function, so we're fine. But what if you have a function that calls another function? What if I had my example earlier of bool I see green, and in it calls the function, it says return is green of sensor val, okay, and then I define my function bool is green int q, and it does its calculations. Well, the C++ compiler runs through your code in order from top to bottom. It doesn't make multiple passes through your code. So when it sees return is green right here, when it sees the function call to is green right here, it hasn't gotten to the definition of the is green function yet, so it doesn't know what that means. It's going to return an error message right there saying that that's an undefined function. So what you need to do is take this whole block of code and move it up here so that that function is defined before it is used. Okay. Good practice is to name functions for what they return if they have a return value. Okay, so notice that my I see green and my is green are valid names for Boolean type variables. They're true, false values. My volume function was simply named volume. It wasn't named calc volume or get volume. It was just named volume, and that's what it returns. Or for its result, if it's a void function. So you might name it go forward, or and so the reason is that way your code can have statements like if I see green, do whatever you need to do. Or it can say if not I see green, then you call the function stop motion, and you can tell from reading this code exactly what's going to happen. If I had named my function something else like motor halt, well, that would still make sense. If I had named it set 0, that wouldn't make so much sense. Or if I had just named it function X, that would totally not make sense. So name your functions things so that when you read your code, the code makes sense. Finally, and this is probably the hardest thing to learn in good coding practices, is keep functions short, keep them to doing one thing. So in my example of the ICGreen function, it read the sensor, but then it called the isGreen function to find out if the color was green. Each of those functions is doing one thing. Each of those functions is relatively short, and therefore it's pretty easy to debug. The longer and more complicated your functions get, the more things your functions are trying to do, the harder your code is to debug, and the less you're able to reuse those functions in other programs later on in your life. Okay, now you know how to use functions. We'll move on from here to advanced data structures.